Hi, Python Padawans. We're back. This is our third lecture in the first unit of material, Unit 1.1. And we're going to talk about computers and programs in this discussion. And in here, we're going to talk about a number of things, including how computer science works, as far as the roles and hardware of software in a computing system. We're going to talk about what computer scientists study, the techniques that computer scientists use, and what computer science actually is about. And we're going to talk about the basic design of the modern computer, a little bit of hardware and software discussion about how computers actually function themselves. We're also going to cover some of the form and function of the programming languages. So we're going to use Python this semester, but many of the principles are the same regardless of which programming language you're actually using. And we'll start actually writing some code in Python. In the first and second lectures, we really just talked about how to structure a program or how to logically think through designing one. But we'll start actually using some Python programming language today. And we'll talk about what's called a chaotic model. And this is actually connected to your first programming exercise, 1.1, that's due this week. So we want to talk about those chaotic models and how those work. So a computer itself is just a machine that stores and manipulates information that's controlled by some kind of a program. And we use computers all the time: grocery stores, smartphones, a gas pump. I mean, even when you stop at a traffic light, you're using a computer. And of course, every time you go to an ATM and withdraw money. So we actually interact with computers constantly. And those computers might not even be personal computers. They might be just a number of types of computers. You know, if you program something on your microwave and tell it to cook your popcorn for 3 minutes, that's working with a computer. So someone wrote the software that operates that. The programs, the software, makes those devices flexible and interactive. So in addition to personal computers, there are some other subtle ways that we use computers on a regular basis, those that I've mentioned, but I'll bet if you think about it, you'll come up with a few more. Just a quick reminder, by the way, all of the notes from these videos are all in your program, your course handbook. A course handbook could be in the bookstores, and you're going to be able to pick up a copy of that. You can order it if you're in the online section. You can order it; it'll ship to you. But if you're here on campus, you definitely want to go pick up a copy of the handbook once it's available, and you'll have all the notes and all the details from these videos available in those handbooks. All right. So what is a computer? Well, a computer is what's called a universal machine, meaning that it can be completely changed to perform whatever function we need. If you think about how computers work and how we interact with a computer, it starts with a computer program. The computer itself is just a hunk of plastic and metal, but the program is what actually makes the computer functional. So a computer program itself is just a detailed step-by-step set of instructions telling a computer what to do. In a previous lecture, in a previous video, we talked about how to plan out those steps. But we can modify the order of those steps. We can add more steps. We can make it more sophisticated. So as we change the program, the computer can perform a different set of actions or a completely different task. The machine itself hasn't changed. Something you're going to do this semester in CS 177, you're going to develop a video game, a full-on game, an interactive graphical video game that prompts the user for input, that interacts with the user with the mouse and on the screen, that has graphics that are animated, that move around. You're going to be doing that this semester. The machine that runs your program hasn't changed. It's the same machine you're going to use to write your papers for your history class or your English class. It's the same machine you're going to use to complete your math homework. And yet, with the program that you develop, you'll be able to play a game on it too. The machine stays the same. A program that you write is executed or carried out. So we put together all the steps in our program. We know what order they're going to happen. We know exactly what we want the computer to do, what decisions it needs to make, whether it's interacting with the user or reading data from a data file and processing it. But it executes those programs and carries out all the steps that you told it to do. And all computers really have the same power with the correct programming. In other words, every computer can do the same things any other computer can do. The programs we write in Python this semester are a great example of that. Python programs can be executed on a Windows PC, on a Mac, on a Unix computer. A lot of Python programs can be executed on smartphones and other computing devices as well, as long as they have the same type of video interface and some sort of keyboard or a way to interact with the user similar to a mouse. Now, the power of a computer is that the software, the programs actually control the hardware. And writing that software is called programming. And that's what we're going to be doing this semester. So computers, I'll move this out of the way so we can see it. Computers are to computer science like telescopes are to astronomy. E. Dijkstra said that, and this is so true in that a telescope by itself can be used for so many different things. And a telescope can see blobs of light in the sky, but it can also see details. And it depends on how powerful the telescope is and how the telescope is configured that controls what the telescope can actually do. Now, if we have a telescope that's on a space station out above the Earth compared to one that's sitting on a little tripod on your back porch, each telescope can do basically some of the same things. So in computer science, when we work with our computers, we actually work through this process called design, analysis, and experimentation. Well, that's scientific method, right? And if you're in engineering, in engineering, we have an engineering method. It's actually very similar method and process that we go through. In design, we're coming up with a way to show how a particular problem can be solved. One thing I talked about in the last video, the last lecture, was that we're going to all be solving the same problems. All 280 of you in this class will be solving the same problems. But there's no one solution. There's many, many solutions, and you're each going to develop your own algorithm or step-by-step process to actually solve that problem and achieve the result that you're looking for. The analysis step is how we look at our algorithms and our problems mathematically. Most algorithms come down to some sort of mathematical algorithm, most mathematical formula. Now remember, math formulas don't have to be 1 + 2 = 3. They could be x squared plus 2x minus x cubed, right? They could be very complicated. Or it could be that it involves true and false statements, Boolean type math. So there's a lot of mathematical analysis we can do. We can actually write an algorithm mathematically to make true and false decisions or choose which solution we want just based on this algorithm we're going to create. Now, there are some problems that are not solvable by an algorithm, and that's possible. But most problems that we're going to approach with our program this semester are going to be solvable through some type of algorithm, and you're going to be writing those algorithms. So we have design, we have analysis, and finally we have experimentation. Those problems that are too complex for analysis, we actually need to experiment in a way to get the closest possible solution. Or maybe we think they're too complex for analysis, but as we actually run through the program, we realize we've come up with a unique or a novel way to solve the problem. So we implement a system and we study its behavior, and then we modify the system and we study its behavior, and then we maybe go back to the beginning and design a completely new way to approach it. Analyze the results from that one, experiment, experiment, experiment. And this process is circular, as is most things in science, engineering, and technology. We're going to be running through this process again and again. As you work on your programs in class this semester, I encourage you to be willing to let go of your first design. You might think this is the way that it's to be solved. There are times, though, after analysis and experimentation, you find that your approach is flawed. You want to go back and redesign it. And that's okay. That's actually a part of this process. So underneath the software is hardware, and the central processing unit is basically the brain of a computer. It is, brain is a weird little analogy for it, but it's true. This is what actually carries out basic operations. It follows the step-by-step instructions. It performs the calculations. It displays the data. It inputs the data from the user. All this is done by the CPU following the steps of the program that it's executing. Inside the computer, besides the central processing unit, we have memory, where it stores programs and data. So when you load a word processing document, you're loading all the text and graphics of that document into memory, and then you can work with them. When you load a program, you're loading all the content from that program into memory, and then you're executing them. So the central processing unit can only directly access information that's stored in memory, or they call it RAM, or random access memory. And that memory is very fast, but it's volatile, meaning if you lose power, you lose whatever was in main memory. So we also want secondary memory or storage that provides us with a more permanent place to have our data, like a hard drive, a floppy drive, an optical CD, maybe a thumb drive, something like that, or a DVD. So we have a number of different types of memory that are involved. But again, the CPU needs to be able to access that memory in order to actually accomplish its tasks. Of course, in computers, we have input devices like keyboards and mice, microphones, cameras, like the camera that's recording this lecture right now. There's a number of input devices that pass data and information to the computer. The computer can work with it. And output devices as well, like video screens, printers, speakers, and such. So there's a number of different types of hardware elements that are included. The central processing unit actually goes through a cycle, the fetch execute cycle, where it gets the first instruction it's going to execute. It decodes the instruction, appropriate action is then carried out, and then it goes back out, gets the next instruction, decodes it, executes it, and repeat, repeat, repeat. Computers are actually rated in the number of times per second that they can go through this fetch execute cycle. And modern computers execute programs in the billions of times per second speed. So in 1 second, your computer, 1 or more billion, 2, 3, 4 billion times has gone through this fetch execute cycle. It's really hard to wrap our minds around that computers are this fast, especially with how small they are. You know, if you have a smartphone, an iPhone or something like that, these things are executing so many commands constantly that to us, it looks like they're simultaneously accomplishing dozens of tasks. In fact, they're not. They're accomplishing one task at a time, billions of tasks per second. So to us, it looks like it's all simultaneous, right? So a programming language is used to write instructions for the computer to follow. And our programming language that we're going to work with this semester is called Python. And a programmer, like you, is going to refer to your program as computer code. Generally, we do. So, if you're asking questions and you say, well, my code has, or in my code I used, that's pretty typical to refer to the program that you've written. The process of writing an algorithm is called coding. And again, we'll use Python this semester to code all of our programs for this semester. All right, so there are several types of programming languages out there. High-level languages, which are designed to be used and understood by humans. Python is a high-level language. Low-level languages, which are only understood by computers. So what happens is we actually write our programs in high-level languages. And then tools like IDLE, the Python utility that you install on your computer, converts those high-level languages to low-level languages that the computer can actually execute. So when you install IDLE for a Mac, it converts the Python to Mac low-level language so the Mac can execute it. If you install Python for Windows, it does the same process, but it converts it down for the type of computer that runs Windows or Unix or whatever it is. So that low-level language, we're not going to be writing in machine languages this semester. We're going to be writing in Python because it's a lot simpler and it's portable between different types of computers. Interpreted programming languages like Python simulate a computer that understands a high-level language. It actually converts it from this simplified Python type code down to something that makes sense and can be ported between different types of computers. The source code of an interpreted language is analyzed and executed one line at a time. Interpreted, one line at a time interpreted. Imagine if you just naturally understood 5 languages, right? So I could speak to you in Spanish, or maybe I could speak to you in Korean, or I could speak to you in German or English, and you could just understand it naturally, right? But if you were just learning one of those languages, and I spoke to you in that language, maybe I spoke to you in Spanish, you would have to stop and think. You literally convert each line that I stated into the language that is more natural to you. And when you are learning multiple languages, the ability to understand conceptually each language is something that happens over time. Computers do not do that. Everything must be brought down to the low-level machine code language. So an interpreted programming language like Python is not the fastest programming language in the world. In fact, it's a little bit slower than a lot of other languages because the source code has to be interpreted and converted to machine code. While it is slower, It is, as I said, cross-platform compatible. You can write the program and it'll work on a number of different types of computers. When you start Python, you'll see something like this. Now yours won't say 3.1 something. Yours should say 3.8 something. You want to get at least Python version 3.8. It'll talk about in this little, in the interactive terminal window, it'll have some details about the version that you installed, and you'll get these 3 little greater than prompts. Those actually show you that it's ready for you to give it a command or a statement. So for example, at the 3 greater than signs, if you typed in print in parentheses hello world, it's going to print hello world. Notice I didn't just say hello world, it says hello comma space world. Everything in those quotes is going to be printed literally, exactly the way that it's shown in the quotes. If I said print 2 plus 3, if you think about your algebra skills, right, everything in the parentheses gets analyzed first. So 2 plus 3 is 5. It's not in quotes, so it's going to analyze it, and it's going to print 5. If you said print, in quotes, 2 plus 3 equals, it's going to literally print this text and then analyze this, and this is what you'll get. 2 plus 3 equals, there's a little space here, 5. Why is there a space here? There's no space after the equal sign here, but there is here. This little comma tells the print function, print this string, and then a space, and then the 2 plus 3. This little space means nothing. It's the comma that is adding this space in here. So print 2 plus 3 equals, then a space, then analyze the math formula 2 plus 3, and the result is what gets printed on the line there at the end. So Python is literally doing exactly what you tell it to do in the order you told it to do it, following its syntax. So as we write our programs, we write them in pseudocode, and we think about how to organize our thoughts. Now, pseudocode is this very detailed but human-readable description of what a program does. It helps you to write pseudocode prior to coding. So you don't have a partner right now, but go ahead and grab a piece of paper so you can do the next couple of exercises. If we want to plan a program that converts measurements from inches to centimeters, maybe our pseudocode might be first comment, remember the pound sign is a comment, prompt the user for inches, then multiply by 2.54, then display the results as centimeters. So these are the steps that we want our computer to follow, right? You might want to write those down on a piece of paper. So how about if you were to write the pseudocode for the following 3 programs? First, convert temperatures from Fahrenheit to Celsius. Well, if we look at our example here, for converting from inches to centimeters, it was prompt the user for inches, multiply by 2.54, display the results. What if you didn't know the math algorithm to convert? You could just say here, convert inches to centimeters, right? And then display results. On this one, convert temperatures from Fahrenheit to Celsius, the process should be something similar, right? Prompt the user for the temperature in Fahrenheit, convert to Celsius, display the value in Celsius. How about prompting the user for their birthday and determine the number of days between today and the user's birthday to calculate their age? By birthday, I don't mean August 24th or whatever, I mean their actual birthday. So if their birthday was August 24th, 2002, then calculate the number of days between that and today. That's a pretty complicated formula, but what does the pseudocode look like? Prompt them for their birthday, calculate the number of days, display their age in days, right? You might even do a little math, display their age in days, display it in months, display it in years. You could do any math you want to once you have the number of days, right? How about if you prompt the user for 3 quiz scores and then calculate and display the highest score, the lowest score, and the average score? So let's look at some solutions to these 3 problems. The first one, fairly simple. Accept the temperature in Fahrenheit, convert it to Celsius, maybe display it, right? The second one, enter the birth date, so prompt the user for their birth date. Figure out today's date. If you want to prompt the user for today's date, you could do that. Or it might be that there's a function or some kind of built-in Python tool that determines what today's date is. Then you count the number of days between today and their birth date and based on the number of days, you can display that in any formula, in any format that you want. Now remember, we're not writing any Python here. We're just looking at how to organize our programs. And the third one, accept 3 scores from the user. Prompt, determine the highest, the lowest, and the average. The average is those 3 scores added together divided by 3. But even if you didn't know what that algorithm was, you could look it up, right? And then display the required crowning, whatever your calculated values are. So these are some solutions to these 3 challenges. All right, that's it for this video. What we're going to do is you're going to go and answer the quiz questions that are based on this third video for this week, and then go work on your homework assignment. So homework 1-1, go work on that and work on programming exercise 1-1, and make sure that you follow the due dates very carefully, that they're shown in Brightspace. They're also shown at the end of the syllabus in a schedule of assignments, and just keep working along. All right, have a great day.